Wikipedia page for comparison of BitTorrent clients. You can sort on Linux and you can sort on magnetic links and see if there's anything.
The Wikipedia? Do it quick before they shut down the internet.
Wait,
Talk about
school has
cisp453?
good internet that actually works
No,
90%
about
of the
torrenting.
time?
Alrighty. So let's go ahead and talk about Socket 4, which is your final, last homework assignment. I can see myself frantically grading at the end of the semester, like night and day and night. As much time as I can allocate. Sorry?
You give it 100% if it compiles, 75% if it doesn't.
Or just look at it. Just WC the source file. Look at the number of lines and the number of characters.
There's the number of characters, there's the number of points.
It's the good old bucket method. You'll see how far you can throw a report into the buckets. You'll have A, B, C, D, F buckets behind you. F being the closest if it drops like right away. I think it's the A. The A is the closest one because it's the heaviest, so you cannot really throw it. And then the furthest one, it would be the F because you can throw it the furthest.
If you run out of time, just assume that the percentage that we already have is the percentage we would get.
Yes, I love it. Since he's
You
only
guys like
grading
that
2
idea.
They were both 100.
All right. So this is our last homework assignment. It's based on Socket 3, and this one is different only because it uses pipes, as the input and output from the programs. You still have to create 4 processes, but you don't use standard in and standard out anymore. You have to use named pipes to do it. There's a quick and easy way to map your pipes, the named pipes to standard in and standard out. So for the most part, you don't really have to change your program much regarding the use of named pipes. So overall speaking, you have to, outside of the program, you have to create 3 pairs of named pipes, so 6 named pipes altogether. Yep.
We thought that it was actually something the program was supposed to do. Is that not something that's expected?
It may be a little bit more difficult to create named pipes from within the program. We haven't really talked about how to do it yet in this class.
We just read the man page.
Yeah.
MK50? Yeah. But you can do it outside. Sorry?
I can delete that logic if you wanted to create it.
Or can we just do it either way?
Do it either way.
Okay.
So that if it doesn't exist, does your program check whether those pipes are already there or not? Or do they just try to create it anyway?
I'm planning to add that.
We had a discussion about the
If square bracket dash E,
Yeah.
You
I
can-
don't want to invoke bash.
wrap your program with a bash program, bash shell. Hey, that's system programming right there. Use whatever tool is available to you for the job. So anyway, so it's up to you guys to choose, how you want to create the 3 types of named pipes. If you haven't started with a program, you can use MK50 is confusing because it's both the command line name as well as the system call name. They're both MK50, and they're used about the same way. So it's up to you to decide whether you want to do it inside your program or do it outside of your program. The program will start without any arguments. You can make your own. You can make yours have optional ones, like number of clients, timeout periods, and etc. So those are definitely optional. But you should start without needing any and defaulting to the optional ones so that they are consistent with this description. So if you want to make your program so that you can have a different timeout period for testing purposes, because 5 seconds, 10 seconds may be too long, and you want to make yours to time out in 1 or 2 seconds, you can change my program, the part that parses ARGV and parses ARGV, just add your own option so that you have a global option of how many seconds you want to use as the timeout to make testing your program easier. And that's definitely optional. But in the absence of dash timeout or whatever you want, however you want to name your option, the default has to be consistent with the description. That's the only requirement. The first process will always act as the server, but it's also responsible to create 3 child processes. And that's why we need the named pipes, because now we are using one single program. We start with only one single program, /main or socket3 /socket3, and it has to spin off 3 additional processes. So the server is one, and then the 3 client programs are also created automatically from the same program. Are we doing okay so far with the idea of this homework assignment? And that's why we cannot use standard in and standard out. Because if you remember from our discussion about processes, when a parent process creates a child process, the file descriptors are shared. In other words, the parent is using, let's say you're redirecting from a file as input, the child will inherit that from the parent. And that's why we cannot use standard in and standard out to test the program. The Unix socket for server-client communication should be named sock, S-O-C-K, in the same folder as the executable. This time is a little bit easier to deal with because both the client and the server are in the same program, and they can both make the assumption that the file name is SOCK sock. So that means you don't have to supply, dash, an option to specify the socket name. It is all built into the program. If you have any questions, just stop me and we'll talk about the confusing point. Be careful when the client processes are created. So the question is, do you want to do it before or after the socket is bound?
Yeah, this part's confusing.
Okay, bind is the call. So the question
You
is
wanna do it
before or after you bind.
You want to do it after, right?
Yeah, I try to do it after, but then.
Well, if you do it after it is bound, after the bind call, okay, who has to bind?
Server.
Server.
Only the server has to bind. Okay. Yep.
My thought was, and I've been trying to test this, but I got a little sidetracked with the double bind thing. My thought was if you have the bind call happen first, the file descriptor should be open to the right socket on all 4 processes. But I suppose at that point.
But you
don't
still
have-
need a connect to open up a socket connection.
Right, you get your file descriptor from Connect.
Yeah.
So on the server side, you can just ignore the file descriptor if you want to. In the child process, in the client process, you can just say, hey, this is the bind socket or the add. Okay, remember in bind, the file descriptor is just the name of the connection point. It's not an actual active socket that you can use for communication. So a child process can just say, okay, this particular file descriptor is not useful to me, and I'm not going to use it for anything. You can just ignore that in a child process. If you think about it the other way, what if you do not call bind before you fork? So you basically create child processes first, and then the parent process will call bind. Then you have a race condition.
Yeah, that's what
Right, that
happened
was
to
our
me. Is I was hitting the race condition where
Yep.
my client process was trying to connect before the
Right.
server client bound and listened.
Right. So in that case, you can have a retry, like a timeout and a retry type of logic, but it's just something in addition. But if you call bind first, then by the time you have your child process up and running, that interface is already there. So, yep.
Wouldn't you have to call listen first or as well, or is it?
Oh, yeah.
I don't understand. I'm
I
trying
had
to figure out
the
all
way I
that.
wrote it. I had
Yeah, you have to call listen too, because otherwise you have the named socket, because bind will actually create the named socket. But when other processes try to connect to the named socket, the connection will fail, and I think it will report back
-1.
connection reset by peer.
Yeah.
That's because the server side is not ready to listen to that particular named address yet, a named socket. So you have to go through both bind and also listen. But the key point is you have to kind of think about the ordering, because when the client gets control, the first thing they want to do is connect. So in order for connect to work, you need both bind and listen to have worked already. Okay, so on the client side, there's not a whole lot of changes to the client side except for the boldface part, which at some point I think I wrote it down in boldface because the alternative was not working. But we'll read the man page and then we'll figure out that part. Each client needs to know whether it is the first, second, or third client created by the parent process. That is not difficult. Okay, because when you go through a loop to create the child process will know the index or the counter that you use in the loop. If you use 3 different fork commands, it will also know which fork is creating itself. So the child always knows whether it's the oldest, second, or the youngest child.
Just make sure in the loop you're not creating more children if you're already a child.
Correct.
As you're about to.
Which means, because in that case you end up with grandchildren and grandchildren if you're talking about the first child.
You find the power of exponents very quickly.
Yeah. And they all try to make connections to the server process.
Oh, you won't get that far.
Someone has tried it.
Yeah.
All right. The first client would use the named pipes called C1 in and C1 out. The second child would use C2 in and C2 out, and then the third one would use C3 in and C3 out. The first client should read from C1 in, and for some reason, I wrote down here to use read-write as the flags. When you're reading from a pipe, you should be reading it only as RD, RD only, and not read-write. And I think we tried it also, in an earlier class, I used name pipes as an example. Remember the pump example that I wrote? That was a name pipe, example. And in that example, I was using read only and write only already. And so we know that read only and write only should work. So let me change this one so it doesn't say that, because the man page says, this behavior is undefined. But at some point, I had to put it in and even put it in boldface. So
I think
It's only undefined for POSIX, it's not undefined for Linux.
Yeah.
right, but it really should not be needed.
Right.
So I'm changing the notes here, making sure that we open up the due date. Let's make it due next. Let's see, next Wednesday is what? It's already in the final week, right?
Right.
So next Monday, we can make it
No,
due on
next
Wednesday.
Wednesday's not
Next
final.
Monday's not.
No,
It better not be.
No.
finals are start on the 11th.
It's the 9th.
It's the 9th? Okay, so we can make it due on the
It's the
9th.
last day of class.
Let's do it. Last day of class. I don't think it's going to be very difficult. I think we can all do it. Famous last words?
Yeah.
Yep.
When we're all crying next Monday, you'll know.
Yeah. Well, let me finish describing the homework, because at this point, I think it is okay so far. Are there any questions, any particular concern about this homework assignment? We are at this point here. No.
So
Yep.
are you gonna, basically you don't wanna start forking inside your server once you're, I'll have to think about it some more.
Okay. Well, you have to think about what happens when you create a new process. The new process wakes up from the fork call. Can determine I'm a child process. So what is the child process going to do at that point, and what do you need for the child process to be able to succeed through what it has to do? So that's what you need to think about when you want to position, when to create the child processes. If you create too early, then what the child process needs in order to make the connection, those resources may or may not be available. If you create it too late, then the process is already in the server mode, so you have to get out of the server mode, get back into the client mode. So that may be that may need some time too. So you have to kind of think about at which point do you want to do it. Okay.
I'm kind of confused about the socket sock and the named pipes. What communication is going on in each of those instances?
Okay, let's see if I can clarify that with a picture. Picture. What would be a good one for a picture? Okay, where's Inkscape? Do you see that?
Yeah, Inkscape is there in the middle.
Oh, right here. All right, so we'll go ahead and try to draw some pictures here because hello. Okay, so let's say this is our server process. Okay, the server process has only has one point to make connections or communication. It's the named socket sock. Okay, so we'll go ahead and create sock here. Some text in it. The color is not working out. Change the color. There we go. It's better. Now the server will communicate through SOC with all the client processes. Let me draw that picture. Draw here. Yeah. There's no good place to put it. There we go. So now you have 3 child processes. So we'll use circles again to draw the child processes. 1, 2, and 3. Each child process will use SOC to talk to the server.
That must be the youngest child.
Smaller. Youngest one is not always necessarily smaller.
That's true.
Usually it's the most intense. Or require the most attention. Alright, so we will go ahead and make some connection points. So we have, so the socket is still used the same way as in all our other programs. Okay? All right. Let me zoom out a little bit. Go. Okay, so now we have the other named pipes. We have C1 in, C1 out, C2 in, C2 out, and so on. So those are name pipes. And we'll go ahead and select a new different color. There we go. We have 3 pairs of those name pipes. Just add the text, I have to do it this way. So we have C1 in, and then we C2, C1 out. So what your program has to do is to do it this way. Pictures. That's basically how the picture looks like, and you can see the same thing for the other 2 child processes.
So the C1 in and C1 out is to the terminal.
C1 in, C1 out are named pipes, so they're not really connected to any terminal, but you can use cat, you can use echo, you can use other ways to send stuff into the file and also get stuff out of it. So that means you will have 4 terminals open at any particular, at least 4. You have 1 to run the program to begin with, but that terminal doesn't really do anything after that point because the server program doesn't do any input or output, and it's also being used, to run the main program. So unless you run it in the background, there's really nothing you can do with that terminal. With the second terminal, with 1 more terminal, you can interact with, you can use cat to interact with C1 in, and then you can use another terminal and use cat to interact with C1 out. So that means, with C1 out and C1 in, you can have a cat program to send stuff out to C1 in. So says cat greater than C1 in. then whatever you type should go into the first client process. Then you have another program in another terminal doing a cat coming from less than C1 out. So whatever is coming out of the first client program will appear on that terminal. So potentially you can have 7 terminals going on at the same time if you want it to be interactive, so that you have the first terminal is just running the server. The second terminal to read from C1 out, the third one to write to C1 in, and so on. So you can turn the entire setup back to the same setting as what we had before. Basically it's just fully interactive. But you also have the option of using echo, ECHO, to just send stuff in whenever you want to. So you can say echo and then double quote, this is a test, and double quote, and then use that to redirect to any one of these inputs. Then it will, whatever you redirect it to, it will receive that particular message. Yep.
Is there a man page on echo?
Yes.
Okay.
The echo is just it's just printing whatever it's just print basically. Instead of you saying print, the command line or the bash option is called echo. So I can just demonstrate how that is used here. Okay, I'll do it this way. I'll go to today's folder and use make FIFO, and I'll just call this test FIFO. I'll pretend that this process is one of your client process. So it's going to say cat less than, which is redirecting into cat, test FIFO. Okay. Then I have to open up another terminal and do the same thing, except this time I use echo. And so I can say echo, this is a test to the name type. And with this one, I need a greater than symbol to redirect to the name type. So we have test FIFO here, press the enter key, and then you can see from the other side, it gets it. Okay. Any question about this?
So that way you can just use one terminal and echo it to whichever pipe you want to test.
Correct. But in this case, apparently, if you use echo, it also sends end of file, because otherwise cat would not have terminated. So if you don't want it to terminate, you can just cat to test FIFO. Then whatever you write on this side should appear on the other side. So this is another test. Press the enter key, and it shows up on the other side. You can write some more if you want to.
So in this case, you'd be using the 7 terminal setup. In this case, you'd be using the 7 terminals.
Yes. Then it can it can be fully interactive. And when you press Control D here, the other side will also terminate because it's end of file.
There's I didn't try it out, but that tail call or program. Tail. Does that how does that one work?
You can use tail. Tail is kind of like cat, with the exception that if you have a really big file, tail by default will only display the last 5-10 lines, if I remember correctly, and then it will continue to monitor the file just like cat. So any new content will also show up. So tail will do the same thing. It doesn't show up because I don't have the number of lines necessary yet, I think. So cat seems to work better. You can also use the man page to find out how to use tail.
Okay.
So once I do a Control D and a file, then it shows up. I think the buffer doesn't have enough lines of code, or doesn't have enough lines, so it's not even displaying anything yet. And if you want to learn all the other options of using echo, you can just say man echo. And I don't think there's a way to stop end of file from being sent using echo. So let me check that. End of line, end of file. Nope. Okay. All right. Any other questions? That was good. Okay. But you can potentially write a program on top of everything else to test it. If you're already familiar with Bash or Perl or one of the scripting languages, you can use a scripting language to write the entire test code for this program, because your test program really doesn't have to you don't need 3 different test programs to test this particular program because of the use of the name pipes. So you actually have somewhat more control over the testing of this program when you're using a script to test it. Any questions at this point? Questions? Go back to the assignment. Each client should open the connection to SOC, which is our named socket, that's the Unix socket, and communicate with the parent, which is the server process, just like in socket 3. Whenever a client reads from the input, from one of those C1, C2, C3 in, echo that to the server connection. In other words, C1 in is taking the place of standard in. Whatever the client reads from the server connection, echo that to the output, C1 out. Yep.
Should we be using select to handle that logic?
Yes, it should be the same way as your previous program. From the client's perspective, the only thing that should change is instead of using standard in and standard out, use C1 in and C1 out. And for the other two, C2 and C3. And later on in the description here, I have a description of using dup and dup2. And that's a quick and easy way to fix your old program so it will continue to work in this new program. So when we get to that point, I'll point it out. Oh, that's the next point. Actually, it's just logical. Use a dup2 so that your C1 in and C1 out will become your standard in and standard out respectively. Then you don't have to change the code of your client side, other than adding a dup2 call. Yep.
I had a question about dup2. I must have read it wrong on the man page, because it says that it returns a file descriptor, but then it also says it returns 0 on success.
Okay, let's do a man2 dup. Okay, so we're talking about man2 dup here, and you can see that with the file descriptors, this is the old file descriptor and that's the new file descriptor.
Okay.
But you have to remember which one is copying to which one, because it's cloning. It's actually making a clone of one of the file descriptor, so that both file descriptors will refer to the same actual file after that point. So here we want to read dup2, make new file descriptor a copy of old file descriptor, closing new file descriptor first if necessary, but note the following. Okay, in our particular homework assignment, which one do you want to be your new file descriptor and which one do you want to be your old file descriptor in this case?
C1 in is the new one and standard in is the old one.
Well, look, read the second part. Close new file descriptor first if necessary. In other words, it's copying from old file descriptor to new file descriptor. Which one? Now remember, standard in is currently mapping to the terminal, to the teletype device. So do you want?
We want to close it.
Yep, you want to. This call will close it automatically and then make it the same as the other one. So what you want to do is to make your new FD standard in and your old FD to be the file descriptor of your name pipe, opened for reading in this particular case. Yep.
Did you say it'll close the
New,
one?
yes.
It will automatically, or do you have to?
If it has to. So this is done automatically.
Oh, okay, yeah. All right.
So the call itself will close new file descriptor first if necessary. Or at least that's the way I interpret it. It doesn't say specifically whether you have to do it or not, but from the context, I think the call will do it. If old file descriptor is not a valid file descriptor, the call will fail and the new file descriptor is not closed. If old file descriptor is a valid file descriptor, and in your case, in this particular example, that should be the file descriptor corresponding to C1 in, just in this example. And new file descriptor has the same value, then dup2 does nothing and return new file descriptor. So that's what your question is. When does it return new file descriptor? Is when they're already the same. Okay.
That's what it was. It was confusing. Thank you.
So after a successful return from one of these system calls, the old and the new file descriptors may be used interchangeably. In other words, after this call successfully and you use the right one for the old file descriptor and the correct one for the new file descriptor, then you can use either one. Standard in or the file descriptor of C1in will do exactly the same thing. So that means the rest of your program doesn't need to be changed anymore because you have been using standard in all along with the client-side programming. So do you guys see the advantage of using this call? Without dub2, you just have to change the file descriptor of all your read and the socket and select calls. But with dub2, you don't even have to deal with it. It's like the rest of the program stays the same. So I think it's worth the time to learn how to use dub2 because it just makes it less necessary to change the rest of the program. The two file descriptors should not share the same file descriptor flags, but in this case, you have to open C1in as read-only, so it would have pretty much the same flags. It doesn't say what value is returning. Oh, there we go. On success, these system calls return the new file descriptor. On error, -1 is returned and error num is set appropriately.
I don't know what I was looking at then. I thought
returning 0?
Yeah.
No, it doesn't say anything about returning 0. It can return 0 because if your new file descriptor turns out to be standard in, then it's going to return 0 because 0 is the file descriptor of standard in. But it should not be the case because you want, that's exactly the case because you want your standard in to be your new file descriptor and it returns 0. So you should only be checking for -1. That's the only time when something bad happened. If it is not returning -1, everything is good. Okay. Any other questions about this? Using dub2? Okay, no questions about dub2. We are moving on. Do not close the socket connection and die even if the input file descriptor has closed. Just do not read it anymore. In other words, this is from the client side. Remember, we are still talking about the client side logic here. So that means on the client side, if the socket connection, that means if the input file descriptor has closed, which means you have seen end of file from standard in, don't close the socket connection. Just leave it alone and just don't read from it anymore. So you can use sleep, you can do a whole bunch of other things so that the child process does not die.
Is that what you would suggest is to use sleep?
Sleep, halt. Would halt work?
Because I don't know any of those, so I'll have to use one. So you'd suggest learning sleep?
Sleep. Sleep just basically is a delay, so you can have a loop and sleep in the loop. You want to intercept SIGINT. When SIGINT arrives, print client 1 to 3, depending on which client is getting the signal, is about to die to standard error. Standard error is 2. Okay, that's file descriptor 2. It's shared with all other processes. Then use the default handler of SIGINT to clean up and exit. So there are 2 steps here. Well, 3 steps. First step is to set up SIGINT to go to your own signal handler. Second thing is when SIGINT actually arrives, in your signal handler, you have to print out the message, client blah is about to die, 9 feet character. And then the third step is to revert back to the default handler of SIGINT, clean up, and then exit.
So is that going to be sig action, or can we still use signal?
You have to use sig action to associate your own signal handler to SIGINT. You can use signal to return to the default action.
So does that mean that SIGINT, the default handler SIGINT, is going to clean up, or do we have to do some kind of cleanup?
You have to clean up. The cleanup part is really just closing the file descriptors. So you want to close the file descriptors and then revert SIGINT back to its default behavior. Send SIGINT to yourself again. All that logic, all those actions has to be done within your own signal handler.
So SIGINT, this signal, or our child process has basically its own SIGINT, right?
Yes. So you want to set up the SIGINT handler after you recognize that I'm a child process. Because signal handlers are not shared amongst the child processes. That's one of the things that are not shared,
Yeah.
within all the processes.
remember that.
So you have to do this after the fork call, because otherwise, only the parent process will have sigint, reprogrammed. But the child processes will still be using the default action for sigint, and they will just die right away without printing all these messages. Are we doing okay so far on the client side? Pretty much the same thing. We're just adding, signal handling and a dub2 so that we can handle, C1 in and C1 out for the first process. Questions? Yep, go
Can
ahead.
you give me a hint on writing the signal handler? I use signal in socket 3, so I don't have to write a signal handler.
Right, you want to use sig action?
Yeah.
Okay, so we want to go back to...
I understand the concept of a signal handler, I just have no idea how to implement one.
Okay, so you have to use sig action to
Sure.
create your own signal handler.
Right.
And sig action requires the signal that you're handling.
Right.
In this case, it will be sig int. It also requires, this one is optional. You can pass a null here.
Okay.
Sig action gives you a lot of options. In other words, you can use sig action to set up a new handler for a particular signal.
Right.
And you can have it to tell you what was the previous way of handling that signal. In our program, that is not needed.
Okay.
Because you can always use signal itself to revert back to the default handler of a particular signal.
So call sig action to set up the signal handler, and then call signal to revert back to the default handling of that signal.
Yep. And then sig action also requires you to pass a pointer to a struct sig action. And inside the sig action, are these things. We talked about this one already. For the most part, you don't have to set up anything. You do have to remember to set up the flags so that you can tell the sig action call itself whether you're specifying a sig handler or whether you're specifying a sig action. Because you have a choice. You can either specify one or the other. One gives you more information when you're in the signal handler. The other one does not give you as much information. In our case, the first one is fine. You can just use a signal handler in our case.
So what does that do? You switch it to, like it's responding to a different signal? I just don't understand how the signal handler tells the system how to handle that system, that signal, I guess. Like
Okay.
you have to tell it to do something new.
You have to tell it to do something new. In our case, it will be using dprintf, because dprintf is the only one that allows you to use a file descriptor
Right.
to specify where do you want to send that message.
Right.
So you have to use dprintf, use file descriptor 2 for standard error, and then print out that message and say, okay, this child process is about to die. And then after that, you have to reset the signal handler back to the default action using signal itself, the signal call.
Right.
And then after that, you have to raise the signal, which means you have to use kill to send sig int to yourself again. Okay. Is that okay? All the steps?
I think so. Yeah,
Okay.
that gives me a hint. That gives me somewhere to start.
Okay. Any other questions about this part? Does everybody know how to send a signal to yourself?
No.
Man to kill. In some other classes, this would be a bad thing to say, but in this class, hey, that's exactly what we want. Okay, kill is both the name of the command line, program, as well as the system call. Kill is the way. I don't know why they call it kill, but that's basically sending a signal to a particular process. You specify the process ID, you specify the signal, and that's it. Okay. In this case, you have to send a signal to yourself. So first of all, you have to find out what is your own process ID. Okay. Any questions about that part? Okay. So the next thing is, how do I know my own process ID? And I cannot remember that part, so I'm gonna look it up here. PID of, but that's not a system call. Get PID. There we go. Get PID, get process identification. It returns the process ID of the calling process. So no need to say any more. You can probably just put this call inside the kill call because you're trying to get your own process ID to send sig into yourself. So do this as the last thing of your own signal handler. Do it definitely after you reset the signal handler back to the default action. Okay. Any questions about everything that we have talked about on the client side? No questions? All right. Now you might want to write some simple programs just to test all of these things individually first. Write a simple program. Write a dead simple program that is just printing something in a loop, sleep, print, sleep, print, and then specify the signal handler of sigint to print, this process is about to die, okay, and then the rest of what you're supposed to do in the program, and see if the program will die, normally when you complete the rest of the signal handler. So I would do that first, because if there's any bug, any type of misunderstanding of the calls, then you can isolate the problem because your program is only this long instead of this long. And also being run as a child process that is created by a child parent process, and there's a whole big, a lot of things can go wrong with your homework assignment. But when you write a program specifically just to test something, it can be like this long, and any problems, will show up like immediately, and you can fix it more easily that way too. Okay. Any other questions? I don't want to, demonstrate how to do it because, any demonstration will become the actual answer.
Sure. You already did that with the thread homework. So. With the thread homework.
With the thread homework? Well, but even so, it only applies to people who are paying attention in class.
Or on YouTube. Or on YouTube.
Or on YouTube. But
yeah,
you
but
still
you post the videos so late. So you got to pay attention.
All right, server side. Server side is about the same thing. Broadcast any incoming characters from any client to all three clients like socket 3 and socket 2. Use select on read with timeout while waiting for a client to have at least 1 byte. Now this part is new. Okay. Before we are only timing out on write. Now we also want to time out on read. And we want to time out on read on all 3 clients. In other words, I am keeping track of all 3 clients. When was the last time you got something to send me? Okay, and I will time out accordingly depending on the amount of time since the last time that client had something to send to me. If the server does not receive at least 1 byte from a specific client for more than 60 seconds a minute, send sigint to that child. Use the wait PID call to confirm the termination of a child process. In other words, this time I'm not doing the same thing as last time. Last time, the child process will die, automatically. The server side will have to handle the child, dying, and then say, okay, I'm not going to echo to this child process anymore. This time, you will actually have to do this. You have to get control and actually confirm that the child process has terminated using the wait PID call. Let's go ahead and take a look at the wait PID call. And wait PID. Wait for a process to change state. That's the wait PID call. So what you want to do is to use the second option, which is wait PID. Description. All of these system calls are used to wait for state change in the child process of the calling process. So it's fine because the server is the parent process of all your client processes. And obtain information about the child whose state has changed. A state change is considered to be the child terminated. That's what we want. The child was stopped by a signal, or the child was resumed by a signal. The second and the third options, I don't think will happen in this case, unless you accidentally send a sig stop instead of sig in to your child. In the case of a terminated child, perform a wait allows the system to release the resources associated with the child. If a wait is not performed, then the terminated child remains in a zombie state. And that's why, when you use the PS call, sometimes you will see, a process, flagged as zombie. It's because it's still, taking up the system resources because the parent is not acknowledging the death of the child. And this almost sounds like a child, a psychology class, dealing with grief and stuff.
Or maybe.
Horror movie.
We were discussing in lab how long it would take for the Los Rios police to show up because we were talking about, did the children know that we killed the parents?
Process.
I want to take the YouTube video and cut out that section and just send it to like the dean of anthropology.
That would be fine. You know, psychology. Yeah. Send it to psychology. Send it to the police campus police. I think something's wrong with my professor. It's all written in the man page. I mean, you know, I didn't invent this stuff. Okay, if a child has already changed state, then these calls return immediately. Otherwise, they block until either a child changes state or a signal handler interrupts the call. So you have to be careful here, because if your child process is not killing itself, is not sending SIGINT back to itself, or the signal handler has not been reset back to default, it will basically keep doing that in an infinite loop. Because you still have your signal handler to handle SIGINT, and inside the signal handler, it is still printing, you know, this process is about to die, and then regenerate the signal. If you forget to change the signal handler back to the default, it will keep doing this until I think it will run out of stack space first, because each one is stacked on top of each other, so it will basically run out of stack space at some point. Then the child process will die in that case. But I think it will take a long time to run out of stack space, you know, with this stuff.
Way to do it. Kind of a messy way to do it.
A messy way to do it. Yep. So the child process is saying, you know, if I'm dying, I'm dragging everyone down. I'm taking everything with me. The stack, the heap, everything. So there you go. You know, wait PID, and then you have to pass a few things. PID is the process ID of the child. Okay, wait, we're talking about the parent here, so get PID is not going to do us any good, because get PID only returns the PID of the calling process. This is the parent process. We want to find the process ID of the child. Where do we get that?
When we do the child
Fork call.
Yep, exactly. So you have to keep track of that. Do we have a good place to put the process ID of a client?
In the struct.
In the structure. So we are all set up for this already. We just have to add additional members to that structure, keep track of a little bit more information, like the read time out, how much time, you know, since the last time we have read, and so on. Okay. This is a pointer to an integer only because in C we do not have pass by reference. So just give it the address of a particular integer, and then with the third one, which is option, we have to read, you know, what option we should be using. Wait and wait PID. The system calls suspends execution of the calling process until one of its child terminates. Okay, that's wait, you know, but we don't want to use wait. We want to use wait PID because we know which child is about to die. Because we know the one that is, because we are sending SIGINT actively. The parent is sending SIGINT, so we know which child we should be monitoring. We should not be monitoring all three. We should be only monitoring the one that we send the SIGINT to.
And the server has already sent the SIGINT at this point, and this just
Right.
wait PIDs to make sure that the child killed itself properly.
Acknowledging the death of the child. Yes.
All right. The suicide was clean. And
Yep. The plastic bag is there.
taken care of. All right.
Yep, taken
That's
care
some
of.
tough parenting.
It was a good funeral.
Interrupt. Interrupt out there.
Yep, closure. Okay, how about closure? Okay, closure call. The wait PID system call suspends execution of the calling process until the child specified by PID argument has changed state. By default, wait PID waits only for terminated children, and that's fine with us, okay? Because we are only waiting for a child process that has terminated. But this behavior is modifiable using the option argument as described below. Okay? The value of the PID, -1, or less than -1 means wait for any child process whose process group ID is equal to the absolute value of PID. We don't have to deal with that. Meaning -1 is going to wait for any child process. We don't want that. 0 means wait for any child process whose process group ID is equal to that of the calling process. We don't need that because we want the last option. We want the actual PID as the argument to PID. The value of option is an OR, bitwise OR, of 0 or more of the following constants. Return immediately if no child has exited. Do not use this because we do want to wait until the child process has terminated. Second option, also return if the child has stopped. We don't have to look for that because we are not stopping the child process. Wait continue also returns if a stop process has been resumed by delivering the signal. That's also not something that we need, so that means 0 would be the last option. For Linux only, we have the other ones. Don't bother with the other ones, just use a 0 for that. Any questions? Now we have status. Okay, so this is a pointer to an integer. When the system call, when wait PID returns, the integer pointed to by this pointer is going to have a value. To understand that value, you have to go down here and then use one of these macros. This returns true if the child terminates normally, that is by calling exit to, or by returning from main. Exit status returns the exit status of the child. This consists of the least significant 8 bits of the status argument that the child specifies in a call to exit. I don't think we have to really wait for, look for any one of these. I think the last one should probably return true because returns the number of signals that caused the child process to terminate. This macro should only be employed if if signal it returns true. Okay, I skipped one, sorry. So this is the one that should return true because the child process should be terminated by the second SIGINT or the SIGINT that is sent to itself, but nonetheless it is going to be terminated by a signal because it is a SIGINT. So this condition should be true. You don't have to check for that, but I think if you want to check for that, that should become true. So then,
what was the one that we're looking for that was the continue or continue?
Continue and stop. We don't have to wait. We don't specify those.
That we're doing no.
Those are options.
This is for ptrace, or what was this for?
These are for options, and options is the third argument.
Okay, it's the third one.
To wait PID, and we can just specify 0 because we are not looking for anything specific, or we are not changing the behavior of wait PID in any way. By default, wait PID only looks for a child process that has terminated by a signal, and that's exactly what we want. That's all that we need to specify.
Yeah, we're assuming we're not going to come back from wait PID unless the child died properly. Is that true?
Correct.
We're just going to be sitting there. So actually, just the fact that we came back normally from that process
Right.
kind of shows us we were okay.
Right. Well, the return value also tells you whether you return normally or not.
Yeah, you have to put the status though through that with signal, I guess, to
Right.
get it to know.
Yeah, you can check the return value because on success returns the process ID of the child. You can check that easily because you specify the child process to begin with as the first parameter. When it returns, you just have to check it is the same value. If it is the same value, it returns it's success. It was a successful operation. If not, something else has gone wrong.
And that's so.
But even if something else has gone wrong, there's not much you can do at that point. Yeah.
So we want the with signal to be the status, or that's.
The status is something that you pass. Is the address of an integer that you pass to wait PID. When wait PID returns, you can check status to see how the child process terminated. So we don't really have to check for anything, but you should confirm, at least if you want to, you can confirm that the child was terminated by a signal. Any other question?
Yep. Would you go over the logic again about the difference between this program and socket 3 as far as sending the signal?
Socket 3 does not send signals.
Right, it just, the server receives EOF from the client
Correct.
and then closes it.
That's because the child process will die, and in the process of dying,
It sends EOF.
it doesn't send EOF, it closes the socket connection to the server.
Okay.
So when the server tries to write to the socket that previously was still active,
Right.
that's what generating SIG pipe.
Okay. When
Okay.
it tries to write to a socket that's been closed by the peer, it
By
gets,
the client
by the
in this
client,
case.
it gets SIG pipe.
SIG pipe.
So this time,
And that's because we don't have any synchronization between the client and the parent process, the server process in socket 3. But in socket 4, we have synchronization because the child process, when standard in of the child process has closed, or you see EOF in standard in,
right.
the child process is not going to say, oh, okay, I'm done.
Okay.
It will just sit there doing nothing and wait for the parent to send a SIG into it. And then it will print, this process is about to die, and then it will send SIG in back to itself to die. But the parent, after sending SIG in, will do a wait PID. So this entire process is synchronized. We have full handshake. A handshake, in communication means, both sides of communication will have, the sufficient protocol to make sure that things have happened the way they're supposed to.
Okay.
So in this case, we have full synchronization because the child process is basically saying, okay, I got nothing to do.
Right.
So at some point, the read PID, the read timeout is going to happen with that one, because there's nothing coming in from that child process or the client process for over 60 seconds.
Okay.
Okay, so at that point, okay, let me just write down the sequence of events, because I think it will be helpful to write it down, especially for people who are just watching this and not here right now. Okay, so the first thing is, client sees EOF from standard in. I'm assuming people use dub2. If you do not use dub2, obviously the standard in will be coming in from the file descriptor of the name pipe.
Okay.
So I'm making the assumption here. Okay. Clients sit and do nothing.
And it does that by intercepting the signal?
Nope. It just sits around. The setting up of the signal should happen way before.
Okay.
In other words, as soon as you return from fork and you know that you are a child process, you should probably set up the SIG-int handler right at that point,
Okay.
even before you try to connect to the server client socket.
Using SIG action?
Using SIG action in that case,
Okay.
yes, because you are specifying your own handler in that case. Okay, so the client at that point would just do nothing because it's just waiting for the server to send its SIG-int. Okay, server times out client in 60 seconds. Okay, server sends SIG-int to client. Now in this case, it's the same client. Okay, we're talking about the same client. In legal document, I would have said client. Okay, server sends SIG-int to client. Client handles SIG-int from server. Client resets SIG-int handler to default. Client sends SIG-int to self. And then from the client perspective, that's it, okay? Because
Right.
after the client sends SIG-int to itself,
It dies.
it will die because that's the default behavior of SIG-int. Okay?
So if we left out that very first line, we could write a very quick test of our ability to handle all this by just writing just this and have the client actually implement nothing.
Yes. You can also use, on the command line, you can say kill dash SIG-int and then the process ID. So the SIG-int doesn't have to come from a parent process. It can come from any other process.
Right.
As long as you own the process, you can always do that. So I should also insert here and say server waits on wait PID. Okay. Server continues from wait PID, changes state of client in data structure, and that should be the end of the handling. Is that helping?
Yeah, so just, I'm sorry, I'm trying to get it.
No, go
So,
ahead.
Client sits and does nothing in socket 4, whereas in socket 3, it sees EOF and just dies right then.
In socket 3, okay, let me just make it clear. This is for socket 4. In socket 3, client sees EOF from standard in, client exits. Okay. In the process, closing the socket connection to the server. At some point, server
Gets
tries.
sick
Oh, okay. Not at some point. The server reads EOF from the socket connection from that client, and the server should mark the state of client. That's one way, but that's the other way too, because when there's no synchronization between the server and the client in
Right.
socket 3, so that means when the client reads end of file, the server may not be waiting for read. It may not be doing a select on read. So you may not catch it this way. If you catch it this way, it's good because you won't get the sick pipe. So that's one way. So I'll just write down here. This is alternative 1. The other alternative is server tries to write to socket connection, gets sick pipe, but we are ignoring that. Okay, and this one is ignored. And then write fails.
Wow, that actually explains some behavior I was getting on socket 3.
So the write fails, and then at that point, the server marks client as dead. Okay, is that helping?
That helped, thank you.
Yeah, because it can go either way. It depends on when the client sees end of file. Because it is possible that nobody is sending anything to the server. The server is sitting, doing a select on read at the time, and when the server is already selecting on read, and this client dies, causing the pipe to close, causing the socket to close, then it will automatically release. It will automatically resume from the select call, because it will say, hey, this client has something to read from that particular file descriptor, but the read itself is not going to fail, but it will return a 0, meaning you are seeing end of file from the socket to this client. So that's one clue to tell the server and say, oh, this client is no longer around. Just mark it as such, so the next time you don't have to deal with it. But it is also possible that when the client dies, the server is actually writing, it has one character that has to be echoed to all the client. So in that mode, the server is not selecting on read anymore. So it is not aware that this socket has closed. So it will get the sick pipe when the server tries to write to the socket connection. And only at that point, the server will get a confirmation, because we're ignoring sick pipe, so that means by the time we get to the write operation, then it will fail at that point. Any questions? Contrasting, how in socket 3 we handle, the client seeing an end of file versus in socket 4, the new homework assignment, what we do when we see end of file. Is it good? Okay. Continuing on, we only have like 2 more points to go. When all 3 child processes are not available, terminate the server process itself. That kind of goes without saying because there's nothing to do at that point. If a client times out on write 3 consecutive times, send sick int to that child. So we still have the same thing as last time, except in this case, we send a sick int to that child. Use wait PID call to confirm the termination before proceeding. The timeout period is 10 seconds. So we have two types of timeout. We have timeout on read, and we have timeout on write. Timeout on write is still the same thing, 10 seconds. And if a child process cannot be written to 3 consecutive times and timeout in 30 seconds, basically, then we have to terminate. If we are not getting anything back from one client in 60 seconds, we also time out and kill the child process.
If the child died, you know, an unscheduled death, then,
Like from illness in this case, yes.
well, you know, if it didn't die elegantly, then aren't you gonna wait it? Isn't your wait PID gonna be, you're sitting there?
It
forever?
will still be okay because the wait PID call, it will just return immediately in that case. So you're talking about the child process somehow terminating without the parent process sending SIGINT.
Yes.
So it is an unscheduled event.
Yes.
According to the man page, if I remember and understand correctly, wait PID will just terminate immediately because the child process has terminated already.
Yeah, that's what it says.
Yeah, but between the time that the child process died and the time the wait PID is called from the parent process, the child process will be marked as a zombie when you use PS to look at the state of the process. Okay, all right. So that's your new homework assignment. It's basically just modifications to your Socket 3 program to basically learn how to use, signal handling, and also DUP. The DUP call I think really is the easiest part of the entire homework assignment. But the only part of DUP2 that can be tricky is who is the old file descriptor and who is the new file descriptor. So write a very simple program first, test that out, make sure you know which one is supposed to be old and which one is supposed to be new, because otherwise it'll be very confusing. You think that this process is reading from standard C1 in, is actually reading from standard in of the terminal that started out the entire program. So that can get very confusing. And when you have 3 child processes, 3 clients doing exactly the same thing, that makes it even more confusing because now the same thing feeds to all the 3 different programs, and it will change the focus depending on which process is doing the reading. It can get really out of hand in that case. So write a very simple program, test it, make sure it works, and you're good. Any other questions? No other questions with this program? All right. Hints.
Yes, please.
Hints. Use the fork call to create additional processes. Kill to send a signal. Wait PID to wait for the state change by PID. Get PID to get the process ID of a process itself. Use the time call to get the Unix time in epoch format. That can be useful because you can time when was the last time I read something from this client. So you have a timestamp. Now when you have a timestamp, then you can determine the timeout structure of your select call. Does everybody understand what I'm saying? Okay, let me give you a scenario. Let's say the 3 students of the front row are the client programs, okay? The last time you sent me something was 3 seconds ago. The last time you sent me something was 2 seconds ago. And the last time you sent me something was 30 seconds ago. 30, 2, and 3. Okay? So when the next time I have to do a select on read, what should I use as the timeout for the select itself?
60 minus 30.
60 minus 30 because that would be the most, that would be the closest event I should be looking for. Okay? So after 30 seconds and the select call does time out, I will check the time at that point, and then I will compare to the last time that you sent me something using the system call, time call. Then I will know that, oh, it has been 60 seconds since you last sent me something. Then I will initiate the process to send you SIGINT and wait PID on you. Okay? On the other hand, if if select returns after 20 seconds and you have something to send me right away, I will have to use that new time as your new timestamp. Okay? If you guys don't have anything to send me within that 20 seconds, then your last read time will not be updated, it will stay the same, and your last activity time will not be updated. In other words, I'm using an absolute time to keep track of when a child process last sent me something. Because that's the easy way to keep track of time and compare, okay, are there at least 60 seconds since this process last, sent me something? It's easy to determine in that case. It's just that you have to use an algorithm to find out what is the timeout of the select call itself. That's the only part that requires a little bit of logic. Is that okay?
Well, why do we care about changing it to a string representation?
Sorry?
Why do we care about changing it to a string representation?
Oh, okay, use the ctime then. Ctime call is going to give you the epoch representation. Oh, it's a conversion?
It says it converts it to a string.
Oh, that's right. It's not thread safe, keep a software timer. Okay, let me look up the correct call to give me the right time. Yeah. Date, get time of day. All right, one of these.
Time in seconds, I just saw somewhere.
Time returns the number of seconds, and I don't see that we're ever needing to use that as a string in any way. We should just be able to use the number of seconds.
Time itself? It
Right, so
returns
it
time
returns the
as.
number of
Oh,
seconds.
okay, so it is the correct call already.
So we don't need the C time.
We don't need ctime. But if you want to print it out for debugging purposes, C
Okay,
print
so
can
that's
be
the only reason
useful.
we need it.
Right.
Okay.
Yep. So you can just call time with a null pointer because you're just using the return value in that case. Yep. There you go.
Okay.
It doesn't say how big is the type, time t. So all you have to do is to make sure that you store it in the time t, variable. Instead of using int, don't use int because this may be a 64-bit integer. I think it is a 64-bit integer. Otherwise, the time will overflow in, is it 2048 or 38? I cannot remember, but I think they had to change the number of bits to represent time because if they continue to use 32-bit, we're going to run out of seconds, in about 20 or 30 years. So we're getting ready for the next Y2K, problem way before it happens.
So you can't just do regular arithmetic with the time _t
Yeah.
variables?
Yep. Time t is just one of the integer types. It's just that we don't want to use int32 or int64. We don't want to commit to the actual width. But it is an integer of some kind, so you can use it for subtraction, addition, comparison. They should all work. Just don't even try to store it into anything that is more specific or width specific. And watch out for compiler errors. Because whenever you try to store a 64-bit number into, let's say, 32-bit, the compiler does complain about it because it requires an explicit user cast to get rid of the message. So watch out for warning and error messages. Well, error messages we don't have to watch out for because it just stops the compiling. But warning messages are the worst because it's just a warning message. It will still compile and give you the object file that you need in order to link. So that's why you have to be careful with all the warning messages. There's an option in GCC to turn warnings into errors. Is it W error?
WL, wall, or W?
No,
No.
the wall doesn't do it. GCC-W, I think it's error. Yep, that's it. Let's give it the program. Did I write the program today? No.
No.
That's good enough as a program. Touch test.c. That's a good program. Hey, I can always compile a program that has nothing, right?
There's no entry point for it.
Yep, it's W error. So use dash W, uppercase W, and an error. That will turn all warnings into errors, which means it doesn't give you an object file. You cannot proceed any further until all warnings are taken care of.
There's not even any warnings for trying to compile a blank file.
Because it is valid syntax.
But it's like, oh, I guess control never reaches the end of a non-void
There's
function.
just nothing specified. If I specify nothing, nothing can be wrong. That's why sometimes when my colleague go to me and say tech is all your fault without saying exactly what, then my usual reply is, if it's not my fault, I'm not working hard enough. Because if I don't do any work, it cannot be my fault at all, anytime, anywhere.
I want to write that on the test sometime. No input means nothing can be wrong.
Alrighty, so that's it for today. You guys feel that you can get started with the next homework, Socket 4? Start with test programs, simple, short test programs. Alrighty, so I'll see you guys on Wednesday. And I should not